Okay, let's start today's video lecture. Last time in class we talked about recursion, and I'll continue talking about this today. So we said recursion is a general kind of a paradigm or an idea where certain problems can be solved by reducing to smaller subproblems that look similar. And the first example maybe we saw, first kind of standard example, let's say we want to compute n factorial. So what's n factorial? So computing factorial is, n factorial is 1 times 2 times 3 times 4 and so on. And sorry, 1 second. Right, so computing n factorial is 1 times 2 times 3 times 4 up to n. And the observation is that it has a recursive structure, namely in order to compute, let me write it here, n factorial, we can compute n minus 1 factorial and then multiply it by n. So here's how you would write the function factorial recursively. So if n is 1 or 0, you simply return 1. And otherwise, you compute factorial of n minus 1 and multiply the result by n. So it's a very simple example, but it just shows this idea, right? It illustrates this idea that you can call the function from inside itself. And we said there's two important kind of rules that we have in recursion. One is we always need stopping condition. So n equals 1 is a stopping condition. And two is that recursive calls should be made on smaller objects. So here we should get closer to a stopping condition, right? So we get to n minus, so we call recursion on n minus 1. Right. So that was the first example, and a very simple example, I think. And the second one is computing the Fibonacci sequence. So what's the Fibonacci sequence? So we start with Fibonacci of 0 is 0, Fibonacci of 1 is 1. And then for every n greater equal to, Fibonacci of n is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. So every number is a sum of two previous numbers, right? So every number in the sequence, for example, 8 is 5 plus 3, and 21 is 13 plus 8, and so on. Right. And then in class, we wrote two implementations. We wrote the recursive implementation. Let me remind you this. Yeah, this is the recursive implementation, kind of very straightforward. So it says, if we ignore these two lines, it says, right, n is 0 or 1, then we simply return n, and otherwise we just make two recursive calls, Fibonacci of n minus 1, Fibonacci of n minus 2, compute their sum, and then return. Right. And then when running it, it was actually kind of slow. And we said the reason it was slow because, in fact, we make the same calls many times. So for example, let's say we compute Fibonacci of 8. So we make two recursive calls, Fibonacci of 7, Fibonacci of 6. But then, Fibonacci of 7 actually calls Fibonacci of 6 and Fibonacci of 5. And when we call Fibonacci of 6, it also calls Fibonacci of 5. So, 5 is called 3 times, I suppose. And 4 is called even more times. Right? So this is very inefficient. And instead we said, oh, well, we don't really need to call them every time. And instead we can use an array just to remember the previous numbers. So here's what we do instead. A function called fibarray. And here's what we does. We first allocate n plus 1 numbers. So we use long because we want to store large numbers because Fibonacci grows pretty fast. And array in position 0 is 0, array in position 1 is 1, right? These are the first two Fibonacci numbers. And then we run with I from 2 up to n, and we have two previous numbers and we want the next number. So this is very easy to compute, right? We look in the array in the two previous numbers that are already computed, right? So let's say I is 2. So Fibonacci of 1 and 0 are already computed, so we can compute Fibonacci of 2. And now 1 and 2 is already computed, so we can get 3, and then 4, and so on. And what do we want to return in the end? In the end, we want to return Fibonacci of n. And then, since we made this allocation on the heap, right, we used malloc, we should free the array before returning from the function. And that's exactly what we do. So we free the array, but before we free the array, we need to remember our result, right? So we remember the result, then we free the array, then we return the result. Okay. And let's try to see what it does. So let's say n equals 30 in the beginning. Uh, Compile it. Let's run it. Okay, and both seem to be running pretty fast. But let's take 40, for example. I don't know. There was some delay, but let's take, for example, 45. And I think 45 is exactly where things where we'll actually start seeing a difference. Okay, so fibfast, nothing is going on, right? So fibfast is using the array. So there's literally 45 additions. There's nothing going on. But as you can see, the recursive version takes really long time. And if we write n equals 50, okay, fast computed kind of fast. Yeah, this is the array version. And the recursive version, yeah, it takes really long time. Okay, I'll stop it, but you're welcome to wait, run it yourselves and wait. Okay, okay, so as you'll notice, this fib fast of Fibonacci of 50, it returned a negative number, and the reason for that is uh, I think LD is still treated as 4 bytes, and if I want to treat it as 8 bytes, maybe this will help. Oh yeah, this works. So LLD means really huge numbers, treat the numbers as an 8-byte integer, so that will help. Okay, and this still doesn't work. Let me, okay, there's two more things I want to do. Here is a fun fact about Fibonacci numbers. So actually, Fibonacci numbers have a closed formula. And the closed formula is this. Okay, so it's this 1 plus square root of 5 divided by 2 to the n minus 1 minus square root of 5. I don't know. It's a closed formula. I hope when you do linear algebra, ask your course instructor. They should tell you how to get to this formula using simply linear algebra. And ideally, by the end of your degree, you should know at least 2 or 3 methods how to derive this formula. But maybe I'm being a bit idealistic here. But anyway, this is the formula. If you're curious, ask me. I will tell you how to actually get it. Right. So why is this useful? Why am I telling you about this? So here's an observation. Well, the first term, this is sort of the leading term. 1 plus square root 5 divided by 2, it's like 1.6 or something. I don't know, some number. 1 minus square root of 5 divided by 2, it's actually a pretty small number. So if we look at the calculator, 1 minus, do I have square root here? Square root of 5. How do I make it? 5 square root. Yes. It doesn't work. Nothing works here. Equal. 1 minus square root of 5 is, okay, it's negative 1.2. When we divide by 2, it's like 0.6 or so. Okay. So here is a fact here. If we raise it squared, it's less than 0.2. And why? Oh, and we also divide by square root of 5. So this is less than square root 2. So here is the idea. So what we can do is only compute the first term, compute this large term. And these other guys, they will be less than 1/2, in fact, less than 0.2. So we can simply round the result from here and it will give us the Fibonacci number. Okay, so that's the idea. So we take this number, we compute it, to the power n, and this, it will be so small that we can simply round this to the closest integer. So let's try to do this. So here it's called fib formula. So the base is this 1.618 whatever. So it's 1 plus square root 5 divided by 2. And so the library math has a function called power, which raises base to the, okay, so this computes base to the power n, and then divided by square root 5. And when we round it, we hopefully get the right number. So let's uncomment this, and we'll see how it works. And maybe we don't take n equals 50, but let's say we start with 30. And amazingly, the formula also gives the right number. So if you look here, this print computes the number, with the right precision, right? But then we round it, so we just get rid of the 0.002. So we get the right number. And if we try 40, yeah, again, we get exactly the same result using a formula. Well, because the formula is actually correct, so we should expect the right result. But my point is that, we can simply take this 1.61 to the power n, and we'll get almost the right number up to 0.0002 or whatever, right? Up to some really small fraction. So we can get rid of this simply by rounding. Okay, and here is one last, okay, so that was 3 ways to compute the Fibonacci numbers, right? There was the using the recursive definition, using an array, and then simply using a formula. Okay. There's one more thing about this long and long. So let me do this. Right. So let's look at the second part. So I would like to know what's the type that gives me an integer with 8 bytes. So if I remember correctly, long will give me 4 bytes on my laptop. Yeah, so it says size of long is 4 bytes. But if I try long, yeah, so long will actually give me 8 bytes, which is nice. But there is a more standard way to do it, and the type is called uint64, which means unsigned int 64 bytes, and it's a really huge number. Okay, so the range of it is really huge. And here is how we can compute the range. So we take huge to be simply 1. And here is what this thing does. So it shifts 1 to the, which way are we shifting it? We're shifting it to the left. So for you, I guess it's this way. So we're shifting it to the left by 63 positions. So in the end, the number will be 1 followed by 63 zeros. Okay, so that's what we'll get. And when we subtract 1, we get a really huge number. Oh, so u, I guess, is not unsigned. It's actually signed. Okay. So we get 1 and then 63 zeros, so that's a really huge number. And when we take, minus 1 of that, so we'll get the largest positive number. So with 48 bits, with 8 bytes, we can get this large of a number. And then if we try to add 1 to it, then that's it. there's no larger number than this. Then what will happen? We'll get to the smallest possible number. So if you want to think of it, all the numbers sort of sit on a circle. So on top is 0, and then you go 1, 2, 3, 4, really large number. If you go in this direction, -1, -2, -3, -4, -5, really small number. And between the really small number and the really huge number, the difference is only +1. This is how binary numbers work. Okay, so we have only 64 bits, right? So, and in binary, this is how it works. So you start with all zeros. So you start adding +1, +2, 3, 4, and so on. You get to a really huge number, and then you add plus another one, and this corresponds to uh, what is it? I guess 1 and all zeros. So you get to a negative number, and all these are negative numbers. So -2, -1, 0. So I hope this example shows you how to see these really large numbers. Okay, how to see them in right, how numbers are represented in the right in the memory. And also in the lab, you had an exercise on representations of binary representation of numbers. So I hope all these together somehow helps. Okay, so that's all. I'll comment this out because this is kind of not the main goal. And I'll put this back in. This is the goal. Again, try these things yourselves. And we're moving on to the next topic now. Okay, so we're done with Fibonacci sequence. Right. So we said this is how we compute the Fibonacci sequence. If n is 1, just return, and otherwise, take a to be the base, compute this a to the power n, and then round, b over square root 5 to the closest integer. Good. Okay, let me show you another example of recursion, and this time it's the merge sort algorithm. Okay, so what's the merge sort algorithm? In general, what are sorting algorithms? They get arrays of numbers and then return and then sort the numbers in the array. Here's an idea. And I'm sure you have seen one or two sorting algorithms, maybe more. Here is merge sort. So maybe you've seen it, maybe not. Here's what we do. We take our array of length n, we break it into two parts from index 0 up to n over 2 and from n over 2 plus 1 up to n. And if n is even or odd, doesn't matter. Okay, so we'll break it roughly in the middle. We sort the first n over 2 elements. Okay, we sort this part, then we sort this part, the last n over 2 elements. Now, after steps 3 and 2 and after steps 2 and 3, this part is sorted separately and this part is sorted separately. So what do we need to do? Kind of to merge them. But now the merge part looks easier because this part is already sorted and this is already sorted. Here's a small example. So this is our array. First we sort left half. Then we sort, how do we sort left half? We take this 4, 1, 8 and we sort it. So when we sort it, we get 1, 4, 8. How do we sort the left half? Using recursion, right? We just learned this idea of recursion that you can apply the same function on smaller inputs. So we apply it on half of the array. Then we sort the right half. How do we do that? We take this 7, 10, 3 and we sort that. So this gives 3, 7, 10. And then we somehow magically merge the two halves. Okay, so how do we merge them? Well, maybe a naive idea would be, we start with the second half, we start with 3, and we push it to the beginning until it finds the right place. So we find 3, push it, swap it with 8, swap it with 4, so here is the right place for 3. And then we want to merge 7, so 7 should be swapped with 8, and it found the right place, and 10 is already in the right place. Don't worry exactly about the merge part, and the description I gave you is actually not very efficient. So there's a more efficient algorithm to do merge. But we'll talk about efficiency later. What I will say for now is this is another example of a recursive algorithm. Okay, so we sorted first half, we sorted second half, and then somehow we made the problem simpler so that now this merge algorithm will work. And let me show you how it's done in the code. Actually, it's in the code is pretty straightforward. So we get an array of length n. If n is less or equal 1, my array is of size 1, then there's nothing to be done really, right? The array is already sorted. Otherwise, here's what we do. So we take the midpoint to be just n over 2. We merge the first half. So this line merges the first, it sorts the first half, right? Because it says array, but sort only up to the midpoint, up to n over 2. What about this line? What does this line do? So what this line does is it says, so remember this, we have this pointer notation for array. So array plus mid, which means we don't start the array from the 0 index, but rather from the index mid up to n minus 1. So n minus mid is exactly the number of elements that remain in the array after we threw away the first part, the first half. So after these two steps, the first half is sorted and the second half is sorted. And then we have a function that's called merge that says, sort the array given that the first part and the second half separately are sorted and mid specifies the midpoint. And I will not show you this here, but I kind of encourage you to write merge function yourself. Okay, it's not a very hard function to write. But it's a good exercise. So so I kind of showed you what we did here. Right, so you start from the midpoint, right, from the first element of the second half, and you try to push it to the right location. Right, so you push it to the left as long as needed. So for example, 3 is not in the right place, so you want to swap it with 8 and swap it with 4 until it reaches the right location. Okay, try to do that. Okay, that's one more example of recursion. And the last example of recursion is this space filling algorithms. Okay, so let me first tell you what it does, and then we'll look at the code. So here's what it does. We get a picture, and we want to color, maybe with red, a specified bounded area. And right, so it's known as flood fill algorithm or boundary fill algorithm. And let me use paint to show you what I mean. So I take how does it work? No, it doesn't work. But I want it thicker. How do I make it thicker? No, I can't make it thicker, I guess. Okay, maybe this is good. So I'm drawing some area. Okay, I'm drawing something. And then here's what I want. I want to fill this entire area red. So here's what I want. I want everything inside to be red. I give it 1 point. Oh, everything here is red. Right, so maybe there'll be another area. And maybe I want to fill this green. So I press the button and all the area inside, everything bounded by the black boundaries everything inside becomes green. I hope it's clear what I mean by this flood fill algorithm, right? So I specify 1 point inside, and this 1 point inside, right, it kind of expands as far as it can. So maybe I go like this. It expands as far as it can uh, to fill everything with the same color. Okay, that's my very nice picture. Okay, I hope it's clear what I mean here. Right. How would we write this in code? Okay. So let's say we have three colors, right? So you remember these macros. So white will correspond to 0, black to 1, and red will correspond to 2, let's say. And we'll write this flood fill algorithm. This is the entire algorithm. Okay, really, this is the entire algorithm. So here's what it says. We get the array, and this is its height and width. And we get the starting point, right? So this is the point. Right. Where are you? Right. So this is the starting point. This is where I want to start from and expand from there. Right. So here's what we do. If this point is not white, so this is my stopping condition. If I reach a point that is not white, then I should stop. So not white meaning it's either red or black. Right. So I reached the boundary or this point is already covered. Yeah, I don't need to do anything. Okay, here's another stopping condition. Another stopping condition is my point, I somehow went out of bounds. So my row is less than 0, my row start is less than 0 or more than height, or column is less than 0 or more than width. Okay, so these are the stopping conditions. And if these don't hold, then what do I need to do? So first thing I need to do is put the color red at this point. Okay, so this is what I do. And then I make 4 recursive calls, each time expanding, trying to color the point above me, the point below me, the point to the left, the point to the right. So maybe I'll try to somehow illustrate it here. Let's say I don't have my, my bucket, my field. So instead, let's say I start from, this is my starting point. So I'm going to put red here, and then I try, the point on the right. And then from this point, where do I want to go? Yeah, I want to go somewhere else. Maybe again to the right, maybe again to the right. When I come back, what will I do? I'll try to expand in this direction, expand in this direction, expand down. When I come back, maybe I'll try to expand in this direction. The point is, I'm trying to expand in different directions recursively. Okay, so I hope this picture kind of helps. Okay, so I'm trying recursively. All I remember is my point, but okay, at some point, maybe I reach to the boundary. So if I reach the boundary, I say, oh, this point is not white. If not, I come back because I don't need to color this point anymore. Okay, so I hope this helps. Okay, so again, so there's, just to explain, there is two types of stopping conditions. One is we reached a color that's not white, and two, we went out of bounds. Okay, both of these say, stop, don't do anything, you're done. And then, this is the only line that actually colors everything red, right? Colors 1 point red. And then I have 4 recursive calls. You see, this one says go down, I suppose. So row +1 means, go to the next row. This one says go row above. This one says go to the, maybe this one is to the right and this one's to the left, or the other way around. Right. So here's my question for you. We said recursion needs to have, two important conditions. One, stopping conditions. That's one. So we have those here. And second, the input to the recursion needs to shrink. It needs to become smaller. So here is my question for you. Where is it here that the input to the recursion is smaller than the original input? Okay, so think about it for 5 seconds and then I'll tell you. Right, because initially it might look, well, look, we're feeding it exactly the same array. So, the size of the input doesn't change. So here is what changes. What changes is the area that we need to cover with red. So each time we cover with red one more point, which means that the area that we need to cover becomes smaller and smaller and smaller. So, after we return from these four calls, uh, yeah, the area will be completely covered in red. Okay, here's an exercise for you. It says write some test cases for each function. So for merge, we cannot write test cases because don't have merge. So first you need to write merge, and then need to write test cases. But for flood fill, please create a small array, like, I don't know, 10 by 10 or something, put some random values in it, or maybe not so random, like specific area, and actually debug it. Do it step by step, follow it, and see exactly what it does. I think it's kind of very instructive to see what it does. Okay, that's all I have to say about recursion. Let me show you this amazing picture one more time. Um, okay, so this is what I'll say about recursion for now. We'll come back to recursion in this course, but for now, let's move on to a different topic. And the different topic is measuring performance of algorithms. And here's a question for you, right? So we wrote this function, computing Fibonacci, and one of them was fast, one of them was slow. The question is, how do we measure the running time of algorithms? And there's several ways. There's two, I think, two ways to do it. One is sort of empirical timing. So what's empirical? You run the code and you see what it does, right? So for us, we ran the code for recursive Fibonacci, and we saw that it's kind of slow when n is more than 45 or 50 or so. Right. And maybe we can try different n's, we can be kind of scientific there. And for each n, we can plot the running, we can measure the time, and then we kind of plot how it grows as a function of n. And there is another way to do it, and the other way is counting operations. So here's what we do. We don't really run the code, but instead, given an input, we want to count how many operations we run on this function. Okay, so and assume for simplicity that all operations, like plus and multiply and compare and equal, they all take one time unit. I mean, actually, in reality, it's not exactly true, but just to simplify things, let's say all operations are exactly one time unit. Actual performance is more than just how many operations, because it depends on CPU speed, it depends on sort of configurations of the operating system, sort of memory and cache, and if you have dual core and stuff like that. So it's more complicated. But just for now, we're going to slightly simplify things and assume that each operation takes exactly one time unit. Okay, so here is an example. Uh, so this function, what it does, it gets an array of length n, and it checks if the array has duplicates. So here is how we do it. In the beginning, found is equal to false. And when we found a duplicate, when we find some I and j such that array I is equal array j, we set it to be true, and then we leave the while loop and return found. Okay, we return true. And if we never find the duplicate, then we return false. Right. So the function here's what it does. There is two loops. There is I loop and j loop. So I goes from 0 up to n, and j goes from 0 up to I. Okay, so j is always less than I. And we compare a array in position I to array in position j. If we found them, we return true. If we never find, we return false. Okay, so stare at this algorithm for a second, and then I will tell you what I want to do. I want to count how many operations it really makes. Okay, let's see. So on input of length n, here's what it does. There is three operations outside, maybe I equals 0, declare j, and set found to be false. For the outer loop, so what do we have for the outer loop? There is checking that I is less than n, checking that found is false, checking that setting j to be 0, and increasing I. So that's four operations times n, because for each I going from 0 up to n minus 1, so we have four n many operations. Let's see. For each inner loop, so we fix I, and we have something like four I many operations. So let's see. This is one, checking if j is less than I, comparing found, checking if AR in position I is equal AR in position j, and then incrementing j. So that's 1, 2, 3, 4 operations, and we repeat it I times, right? Because j goes from 0 up to I, right? So for each I, we have four I many operations. Okay. And I think that's all, right? So this 1, 2, 3, 4 was counted for the outside loop. For the outer loop, we counted 1, 2, 3, 4, so that's 4n, and there is 4I for the inner while loop. Okay. So what's the total number of operations? Let's see. 3 plus 4n, and the inner loop, well, this is the hardest one, I guess. It's 4 times 1 plus 4 times 2 plus 4 times 3 plus 4 times 4 and so on. When I is equal to n minus 1, this is 4 times n minus 1, worst case. Right. And there's a little, if you pull 4 outside, you get 1 plus 2 plus 3 plus 4 up to n minus 1. And this is equal to, well, this is the formula when you multiply by 4. Okay, so sum from 1 up to n minus 1 is equal to n squared plus n divided by 2. Or is it minus n divided? I don't know. Not super important. I'm pretty sure it's minus n divided by 2, but I could be wrong. Right. So if you compute all these, the total running time is approximately this. Why approximately? Well, if we might finish early, because if array in position 1 is equal to array in position 2, we'll just exit earlier. But in worst case, this is the running time. And let me tell you what I think about it. I think the n square is the important terms, and the 2n plus 3 are sort of not very important. N square is, think of n as like 100 or something. So n squared is 10,000 or something, and n is only 100. So n squared is really, it's much more important than n. And roughly speaking, if we multiply n by 2, if we double n, then the result will be multiplied by 4. So it will be, it will be 2 times of 2n squared plus, something times 2n plus 3, which will be 8 times n squared. So the point is that n squared is the important term. That's what I want to say. Okay, so if we increase n by a factor of 2, the total running time will multiply by 4. Right. So this was our example how to count the number of operations. And I did it super explicitly here. Usually you skip all this stuff. You say, oh, this is some constant and this is some constant. You don't care if it's exactly 4 or 3. But I thought once it's good to make it very explicit. Right. Later in the course, we'll not care about the constants, but one time I thought it would be good thing to do. Okay. Let's do two more examples. So here is two more examples. write the following function. It gets an array of length n, and it checks if all entries are distinct. Okay, so it returns 0 if all entries are different, it returns 1 if not. Oh, that's exactly the exercise we did previously, right? From the previous slide. Okay. Write the code for it and try to do, we did the running. Here is another example. It gets again an array of length n. And here is a guarantee. It contains all numbers from 0 up to n except for one of them. Well, there's only n cells, but there's n plus one number. And your goal is to find the missing number. Okay, so they're all different, and your goal is to find the missing number. So the question, how fast can you do that? Okay, so maybe pause the video for a minute. I'll count to 5 and I'll continue, but pause the video and try to think about it. And in particular, think what's the running time of each of these algorithms. Okay, so I'll count to 5. Okay, so let me tell you, for the first problem, we saw it on the previous slide, and the running time was approximately 2n squared. What about this problem? How fast can you solve this? So here's an idea. We can solve it in linear time. So linear time maybe, say, 3 times n operations as follows. Compute the sum of all numbers in the array and return n times n plus 1 divided by 2 minus sum. Why is this the solution? So why does this solve the problem? So the reason it solves the problem is the following. Look, if we had all the numbers here, from 0 up to n, then the sum would be exactly this. If exactly one of the numbers is missing, if we compute the sum and we take, the sum of all numbers, compute the sum in the array, then the difference will be exactly the missing number, right? Because the sum here gets contribution of all numbers except for the missing one. So if we also had the missing one, this would be the sum. And why is it 3n? I don't know. Maybe it's really just n plus I don't know. What is it? 1, 2, 3, like n plus 4 or something like this. Anyway, but it's something linear in that. So it's not quadratic, it's only linear. Okay. And let me do 2 more examples. Oh, 3 more examples. Oh, I have a lot of examples. Here's a question. You get 2 numbers, each of length n, and your goal is to compute the sum of 2 numbers. Oh, that's exactly what you got on your exercise, right? And think of it that you get the numbers in Notepad or something. So maybe your first number is this. Your second number is this. Let's say they're both of the same length. And your goal is to compute their sum. How would you do that? Well, if you did the exercise, you probably did something like, compute the units, compute the tens, and there's the carry, and then compute the sum of the units, compute the sum of the tens, compute the sum of the hundreds, remember the carry, and so on. So approximately, this can be done in linear time, right? So maybe like 2n operations or something like this. Okay, what about multiplication? So we get 2 numbers and we want to compute their product. So if you want to compute their product, yeah, if you remember long multiplication, like 25, I don't know, 23 multiplied by 48, if you remember how to do that, you need to multiply 4 by 3, you get 24, you have 2 over carry, 2 times 8 is 16, so you get 18, I guess. That would be in the first line. And then you need to multiply 4 by 23, so 4 by 3 is 12, 1 is carry, yeah, something like this. Okay, and then you need to sum this up. So when you sum this up, you get, I guess, 4 here, 0, and then 11. Yeah, I don't know. I hope I did it correctly. Right. So here's my question. What's the running time of this, of multiplying two numbers of length n? Let's see. If this is of length n and this is of length n, then we'll actually have n rows here, it will not be 2 rows, but it will be n rows. And each row will be approximately of length n, right? Because we multiply one digit by the whole number. So the running time will be approximately n squared and not n. Okay. And here is another example. Let's say you get a really huge number. I know, a huge number like, I don't know, 91 or something. And your goal is to find two primes. Oh yeah, and it's a product of two primes. And you need to find two primes such that 91 is equal to the product of two primes. So for example, in this case, 7 and 13, except that the number n is, it's not as small as 91, but it has length maybe like 100 digits. So how fast can you solve this problem? Okay, so that's my question for you. So this one we solve in linear time. This one we solve in quadratic time. And this, well, yeah, I don't know. You tell me how fast you can solve this. And here's another question for you. So yeah, we can solve it in quadratic time, but can we solve it faster than quadratic? So here's a question. Can you solve multiplication of two numbers faster than quadratic time? Okay, that's all I'll say for today. Thank you all.